Hello everybody, welcome back to another reinforced concrete design video. This one's going to be on compression reinforcement. And this is super similar to what we've already covered in previous videos where we had tensile reinforcement in the bottom face. This video is just touching on that concept a little bit further and talking about the concept of why we even need to add compression reinforcement in the first place. And we're going to use this problem to help visualize what the analysis would be like for one of these beams, but I just want to start off by talking about what is going on and why we need to do this in the first place. So, what we already know about reinforced concrete beams is that if we wanted to make them stronger, we can do a couple of things. The first thing we can do is we can add steel, obviously, to that tensile bottom face in order to provide that steel strength rather than relying on the concrete. The next thing we can do is then look at the geometry of the beam. We can either increase the width or we can increase the depth. But obviously, the more effective approach would be to increase the depth because it will give you a bigger arm between your couple moment um, produced between the CR and the TR, right? However, in real life, there's usually a lot of rules and restraints to designing a concrete beam, one of which being site constraints, obviously, and the other would be the architect or whoever is responsible for controlling the geometry of the beam, specifically the depth, because you don't want to exceed a certain depth uh, in a high rise, for example, if you want a clear space in your area. So what do? We need a stronger beam, but we can't add any more tensile steel because now we're going to be exceeding the tensile reinforcement ratio or the steel reinforcement ratio. We're going to be over reinforced and we can't mess with the geometry. So what do? We need to add compressive steel. And the main takeaway for compressive steel is that it's going to be improving the moment resistance of your beam because you're now considering an additional contribution from this steel in the compression zone without over reinforcing your beam. You're still going to be in that steel controlled failure where we are going to have, that slow kind of failure mode instead of the sudden concrete failure. So that's the main takeaway and why we need to do compression reinforcement sometimes. And the rules for analysis are super similar to what we've already covered previously, where we're looking at the steel and its contribution to the moment resistance produced by that couple between the tensile resistance and the CR. But in this case, we also have that CR prime, which is pretty much just for the steel in that compression zone. And it follows the same rules, just in a different zone. So we have to consider whether we are yielding the steel. So we have that strain and compression steel, which is the epsilon S prime. It either yields where you're exceeding the strain or the max yield strain, which is 0.002 typically. And that's our assumption for design for the most part. But if that doesn't happen, that means we're not yielding the steel. We actually need to consider the equivalent formula for that new stress that's developed or the stress below that of yield stress, right? Because you're not meeting that yield stress that you were initially designing for. And once again, similarly, we're going to check for that assumption. If we exceed yield stress or not, we're going to check it by simply looking at the epsilon S prime and using similar triangles and the strain distribution, we will determine whether we are exceeding that yield strain. Okay. So the formula for the moment resistance, obviously super similar, except now we are adding this CR prime component, which is following the same type of formula for any steel calculation. You have phi s times the stress developed, Fs prime, and then the As prime, which is the area of that steel in the compression zone. Proceeding with the same formula, we have that restricting condition where the TR must equal to your CR plus the CR prime, where CR is your compression block stress or the force resultant, and CR prime is going to be that steel stress or that steel resultant force. Taking all that into consideration, you now have that moment formula where you have the two couples between the CR prime and the CR, with respect to TR. We're going to use this to solve this formula or this problem right here. So let's take a look and see what we're dealing with. Alrighty, so let's take a look at this problem. I picked a super easy one for us today. We have a typical double reinforced concrete beam, and we have 625 Ms on the bottom face, and we have 220 Ms at the top, and it gives us our effective depths. So we have an effective depth for the compressive steel and the tensile steel. So that's going to be important for this formula down here. And it wants us to determine the factored moment resistance, and it gives us all of our variables. We can simply go ahead and proceed as normal, as if it was a typical single side reinforced beam. Another note, these are typically called the doubly reinforced because you have double layers, one on the top and one on the bottom. First things first, we have alpha 1 equal to 0.8 and beta 1, which is equal to 0.9. And we know this because we have FC prime equal to 30 MPa. We know that range where it's between 25 MPa to 40 MPa. These values are going to be typically equal to 0.8 and 0.9. You can check that in the code as well. There's specific formulas for these variables, so if you wanted to check it, feel free to do so. Now the next thing we can do is solve for our unknowns, which is the CR prime and the CR. We're going to assume that the steel is yielding in the compression zone. So let's write out what that's going to look like in our case. So if the steel is yielding, you're going to have 0.85 times 400, which is our yield strength of the steel right there. Then you have the area of the steel. So you have 2 bars and they're 20 Ms, so that's going to be 300 mil as the cross-sectional area. Then solving for that, CR prime is going to be 204 kilonewtons. Then similarly, we do the same for TR, just plugging in those numbers, 0.85, 400. And the area of that steel is a little bit different. You have 6 bars on the bottom times 500 for the area of a 25M. And solving for that, you are left with 1,020 kilonewtons. Now we're proceeding with our A formula to get the depth of our compression block. And we're using that condition once again, where TR must be set to equal CR plus CR prime. And rearranging that formula, you have something that looks like this. So let's see what we get for that A value. We're going to have 1,020 minus 204 times 10 to the 3. That's all over these variables here, so 0.8, 0.65, 30 for the compressive strength, and you have 400, which I should have wrote in the problem. We have a width of the beam of 400 millimeters. Sorry about that. 400 on the bottom, and then that's going to equal to 131 millimeters. Now we need to check and make sure that our assumption is correct, because in this formula we assumed that we used 400 as the yield strength of the steel, which is correct, but we don't know yet if that steel has yielded or met that stress value. So we're going to check what the strain in the steel is to confirm this. So ES prime, epsilon S prime, is going to be equal to this formula here, which is the max strain in the concrete, and then 1 minus d prime over c. We don't have c yet, so let's just go ahead and solve for what c is using this formula up here. We just rearrange it, and we get a over beta 1. That's going to equal to 131 over 0.9, which gives us 145 millimeters. Then we go back and plug into this formula right here. We're going to have 0.0035, and then 1 minus the 50, which is the d prime right here, over the c value, which we just calculated, which is 145. And solving for that, you have a value of approximately 0.0023, which is greater than the yield strength of steel, which is 0.002, right? So that means our assumption is correct, and we are allowed to use the CR prime value. Geez, sorry for the voice crack. That CR prime value of 204 kilonewtons. That means we can just go ahead, go right to the MR formula and plug in for it. So we have MR, which is going to be equal to 204 times 10 to the 3. We have D minus D prime. These values are given, luckily for us. So we have 510 minus 50. And we're also adding the CR component. So that first one was the CR prime component. And then we have the CR component, which is 816 times 10 to the 3. And then the D, which is 510. Then A over 2 is 131 over 2. We have all these variables. Solving for that, you're left with 456 kilonewton meter. Boom. Super easy. As long as you have the assumption that's met, where you have the steel yielding, makes life a lot easier. Maybe in a future problem, I'll show you what happens if we actually do not yield in the compression zone.